This is 335. So I don't have the same right now, but I have a 4-part linkage. So
Same, okay, cool. Just need my favorite.
yeah,
'Cause I haven't done-
exactly. Yeah. So then you would just do that, and then here's what I'm thinking. It's because it's 1 to 3 slides. I think it's supposed to be kind of quick.
Yeah,
So I'm trying to, it's all, this is a good chunk of things. So I'm gonna do
I was.
photographs of assembled, disassembled. I don't like assembled and like assembled and disassembled, like disassembled is this.
Yeah.
Right, so it's like, it feels like these items.
I mean, I
Makes sense.
was thinking. So it's with it versus the map.
Yes, that's exactly what I'm thinking. So I'm gonna do the photograph of assembled, disassembled.
Yeah.
And then I'm gonna have another slide that is calculations and however that looks, and then improvement such conclusions.
Yeah, by hand. Then he said. By hand.
I don't think so. City go with the. No. Any more really good, just include like, and then start.
Cool. I will.
I should go to the meeting. I made it here 5.
Oh, well, then I'll just
I'm not waiting to
do the math. That's fine.
I'm not gonna give it to you. I just need the code in my head right now.
Yeah, and also I am dating Megan Fox. She doesn't go to the school that you would know.
Yep, yep. Okay, so we have. This homework on Friday, and then we have the homework 7, which is the long ass Mathematica, which I'm still trying to figure out a solution to, because I can't do it on any of these. And then the project, I already emailed it saying that it's still not working, and I already talked to them.
Want to see again, bro?
Yeah, and then we have the refrigeration peer review that's due tomorrow. And then we do remember, we all are gonna show up at the same time. Because we have a
Yes.
certain-
Oh, 50 to 130.
Yes.
So I've been trying to figure out how to flash. The GTX to you or Mac Pro 5.1.
I've never heard of that plan. How are you gonna flash it? I'll get it.
Yeah.
Read it?
Yes. I've been on so many forums.
Yeah, I was watching him look.
Okay, I think that's all.
Okay, so what I see is that
Start with something like 0.1, I think. 0.0. Yeah, I think that's a good.
Yeah.
Yeah, and then go based. Yeah, you want to make sure that you change the mesh side, getting it good. Great. Yeah, try that again with the secret. Or let me know how it is. Yeah.
Hello, Dr. Chan, can you hear me?
Yeah, I can hear you.
Um, is it okay if I ask some questions, sir?
Sure, of course.
Um, so just so I understand what's going on, will we be discussing the final exam in today's lecture?
Yes, that is the
Okay.
plan. We're gonna be discussing the final project today.
And then also so I saw in the syllabus that assignment is it going to be assignment 6 is scheduled for this week.
It is, yes.
Do you know when that will be posted on Canvas, or are you still working on that?
I'm still working on it, so hopefully tomorrow.
Sounds good. Thank you, sir.
Yep. Yep. Typically I like to see at least 5 or 6. Yeah, so just 1 or 2 more. $7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? We're good. Good. I might be a little bit low energy today. I was at a wedding yesterday. It was for one of my good friends, so I was the best man for the wedding. So I gave a speech. I drank a lot. I was extremely hungover this morning, and so I'm kind of just barely surviving today. So I'm a little bit low energy. Forgive me. I should be back to normal by Wednesday. Okay, so the plan for today is first thing we're gonna do is we're gonna talk about the final project, and so we'll go over that together. That's not gonna take very long. It is quite similar to your midterm project. There's just a couple twists to it because I can't give you the exact same thing as the midterm project. So we'll go over that for maybe the first 15 minutes of class, and then we'll talk about optimization. And so we're on a short kind of schedule just because we did activity 5, which was originally scheduled for before spring break. We did that last week. And so this week we have another ANSYS activity lined up, for us to do on Wednesday. And so we'll go over kind of the pre-knowledge that you need for that today. And then we'll do the activity on Wednesday. Okay. So because of the wedding, I am a little bit behind on the grading. And so I know I haven't graded activity 4, that is on my to-do list. And so, I'm hoping to have activity 6 up by tomorrow, and then activity 4 graded at the same time as well. Okay, so I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and let me switch to my computer screen here and let's talk about the final project. Okay, so this document is up on Canvas right now. And so if you go to the assignments page of our course website, you'll be able to click on the final project. Okay, you can see its due date. right? And the document that we're going to be looking at is the instructions or the specification, which is this document right here. It's just the first one that you come across. Okay. And just like the midterm project, I have the rubric here. I have the template, you know, as well as some CAD model that you can choose from. But we'll talk a bit more about kind of the CAD models for this project. Okay. And so, you know, your final project for this class is very, very similar to the midterm project. So it's basically going to be, you know, what I consider to be a full finite element analysis. And so you're going to take a geometry, you're going to load it up into ANSYS, you're going to mesh it, you're going to apply the boundary conditions, you're going to do several different configurations. You're going to get your results, and then you're going to write a report on it. Okay. The difference here, or the first difference for the final project, is that I'm giving you the option to choose your own geometry. Okay. So this is the final project for the class, and so you know we're getting to the point where you're going to learn most of the content of what's available in this class. And so I want to give you guys the opportunity to apply it to something that either maybe something that you're working on at work that could be useful for you, or maybe something you're working on for research, or maybe you're doing research for for the professor here at Cal State Fullerton, or maybe it's just something that you're just interested in just in general. So maybe a hobby. Or something like that. Okay? So unlike the midterm project where I kind of forced you to choose one geometry or the other, for the final project, you can choose your own. Okay. With that said, you can if you don't have a geometry in mind, or if you have trouble finding one, I am giving you a couple options here. And so I'm giving you a CAD model for a 2-story building. It's the lamest 2-story building ever. Probably not one you'd ever want to step foot in, but technically it is a 2-story building. Okay. And the globe valve and the shaft housing from the midterm project are also available. But if you choose this, you have to choose the one that you didn't do for the midterm project. So you can't double dip. You can't do the same geometry for the midterm project as the final one, but you can choose the other one if you.
Dr. Chan.
Yes.
Can you scroll down?
Yes.
Are the units listed? Do you want us to use certain units?
Not in particular, as long as you're consistent throughout the report. That's all that matters to me. Yeah.
Okay.
Yeah. And so the third option, of course, is to choose your own geometry. Okay. But if you are going to choose your own geometry, I want you to run it by me first. And so if you have a CAD model for the geometry that you're thinking about, just send me an email, send me a couple screenshots of the geometry. And just give me a little bit of an explanation of kind of what you had in mind in terms of, how you want to angle your analysis, what your objective is going to be, what kinds of boundary conditions that you're thinking about applying. And then I'll give you the okay. Okay. And so, the reason I'm doing this is because, when I kind of let, people choose their own geometry, I get a wide variety of requests. And so, on one side of the spectrum, I've had some people, just CAD up like a cube and say, oh, can I use this for my final project? And I tell them no, because it's the cube. That's way too simple. But then on the other side of the perspective, I sometimes get people with that want to do something that's way too complex. Like they want to do a finite element analysis on the entire Eiffel Tower. And so that is something that's a little bit out of the scope of what we can do in the class, especially with kind of the student license that we're working with. Yeah. And so again, if you're working on a particular system for work or for research, or maybe something that you're interested in, this is kind of your opportunity to apply ANSYS to one of those things. Okay. And so if you do choose your own geometry, you are responsible for finding your own CAD model. I'm not going to scour the internet or create a CAD model for you. And so, you can go and do that. There are a lot of online repositories for CAD models that are out there. And so there's a resource, you can look up something like GrabCAD. And so GrabCAD is a good online website where you can find a lot of CAD models. And so you can find something on there. But of course, if you have a CAD model for something else, you can of course use that as well. Okay. Any questions on this so far? Okay. So let's go over the requirements. And so this is going to look very similar to the midterm project. So I'm going to go through these fairly quickly. Okay. So just like the midterm project, you're going to need to have an objective for your project. Okay. And so, you have to think about kind of what what kind of information that you're looking to get out of the simulation. Okay. Maybe you're looking at, you know, is your part going to fail? What is the maximum deformation? Okay. And so I want you guys to really think about this, because that's one thing for the midterm projects that I saw was kind of lacking in a lot of people's reports is, you know, a clearly defined objective in there, you know, for their finite element analysis. I got the sense for a lot of people's midterm reports that, you know, people were just doing it just because it's an assignment. But, you know, I want you guys to kind of think a bit more beyond that in terms of, you know, why are you doing this? You know, why would someone professionally be doing this finite element simulation? And like, what kind of information would you want to obtain from that finite element simulation? Okay. And so I want you guys to really think about that and really make it clear in your report, kind of what you're looking for. Okay. All right. So finite element modeling methodology. So this is pretty much the same as the midterm project as well. You know, you're going to talk about your meshing, you're going to talk about your boundary conditions, your material properties. Overall, I think I was pretty happy with this with the midterm project. And so, you know, I'm not I'm not going to say too much more on this. The only difference here is that when you report on your mesh and you're reporting on the number of elements that you chose, I want you to do a mesh convergence test for the final project. Okay, so that's one big difference here compared to the midterm project, is that I want you to do a mesh convergence test. Okay, and so, you know, when you're going to choose, you know, the number of elements or the element size, you know, you should have some evidence to kind of back up kind of why you're choosing that element size. And the mesh convergence test is going to be that test. Okay. Okay. And just like the midterm project, you're going to be expected to do 3 different static configurations. Okay. And so 2 of these configurations, they have to have different boundary conditions. And so different loadings or constraints. But the third configuration could just be a change of material properties. So maybe for your third configuration, you use the same loadings as your first configuration, but you change the material to like aluminum or something like that, or to copper. And we look at the change in results. Okay. And just like the midterm project, you know, I want you to do more than just changing the magnitude of the loading. You know, I want you to change, you know, either the direction of the loading, maybe add some additional loading, maybe you change the constraints, something like that. Okay. But I don't want to have 2 situations where you apply a 10-pound load and then situation 2, you apply an 11-pound load. Okay. So that's not really going to give you much of a difference. Okay. Additionally, in addition to the static configurations, I want you to incorporate at least 2 advanced ANSYS features that we covered in the second half of the course. Okay. And so, you know, these are basically outlining all of our remaining activities. And so activity 5, we cover transient dynamic simulations. This week, we're going to do design optimization. The next activity is going to be on modal analysis or vibration analysis. The last activity is going to be on buckling. Okay. And even though we're not going to have an activity for it in the class, if you wanted to run a thermal simulation or a fluid simulation through your geometry, that can count as an advanced ANSYS feature as well. Okay, so I want you to incorporate 2. You don't have to do all 5. You just have to pick 2 and apply that to your model. Okay, but I don't want you, you know, when you're choosing your advanced ANSYS features, you know, again, I don't want you to just choose the ones that you think would be the easiest or think that would be the least time consuming. You know, I want you to choose the advanced feature that most closely aligns with your objective. Okay. And so think about, you know, you know, how your part is used in practice. You know, think about, you know, what would be kind of useful information, and what would be you know, 2 advanced ANSYS features, you know, that would help you kind of satisfy or kind of, you know, answer the question for your objective as much as possible. Okay. And so just like everything else in the report, you know, I expect you to pick 2 features and I expect you to justify it. So I expect you to say, you know, I chose to do, you know, modal analysis on this geometry, and here's the reason why modal analysis is important for this geometry. Okay. And so, you know, I'm not only looking for, you know, did you use the feature correctly, but I want you to justify kind of why you used it and why you think it's important for this. Okay. Because these you know, these projects, you know, of course, you know, we don't have any exams in this class, and we don't have a final exam. You know, these kinds of justifications and these kind of explanations, that's how I'm basically assessing, you know, how well you understood the conceptual part of this class. Okay? Because a lot of this class, you know, yes, it's about how we use ANSYS, but a lot of this class also, you know, conceptually, you know, do you understand kind of what we're actually doing in ANSYS besides just pushing the buttons? And do you understand kind of why we're doing the things the way we do? And do you kind of understand the concepts and theories behind these features? Okay? And so that's how I'm going to assess your understanding. Okay. All right. Any questions on this so far? Okay. And so from that, we're going to move on to the results. And so the results are mostly similar. And so I want you to show the total deformation and equivalent stress for all the static scenarios. Okay? And so for the advanced features, you should show at least one relevant screenshot showing your results. Okay. And so not all of these features are going to involve deformation or stress. And so I want you to show, at least one screenshot that's from each of those, that shows the results, as well as, a good explanation in the text about, what the reader should be looking for. Okay. All right. So the discussion, just like before, you're going to discuss your finite element results. I have some discussion questions for you here. Okay. So 3 of these, I think, are the same for the midterm project. And so I think, most people did a pretty good job of answering this on the midterm project. But I am adding one discussion question here, based on verification and validation, which is what we're going to cover next week. Okay. So next week, we're not going to do an activity. We're going to talk about V and V. And I want you to kind of discuss that in your report. Okay. And then finally, we have the conclusion. And so that's just about kind of the same as before. Okay. Just like before, I'm going to provide you with a template. And so the template is actually kind of very similar to the midterm project. Because there's some added requirements here, your final report should be longer than your midterm report. And so on average, it's going to be about 16 to 20 pages just because there's a lot of figures involved. Okay. But of course, this is not a hard requirement. So you can add more or less than this, depending on, the nature of your report. So as long as you satisfy all the requirements, I'm not strictly counting the pages, but, I do expect all the requirements to be satisfied and to be thoroughly explained. Okay. Okay. And we have the rubrics. Teams, there are no teams. This is an individual project, so everyone has to do their own simulations and their own report. Okay. And just like the midterm project, please don't hesitate to reach out to me. If you're having issues with ANSYS, I'm always happy to help. And we'll kind of go through this just same way as the midterm. Okay. And of course, you have a bit more time for this project compared to the midterm project. So the midterm project, I think I gave you about a month. And so, the due date for this project is going to be May 22nd, which is the Monday after finals week. And so you have about just about 6 weeks to do this project. Okay. Okay. And so that is the final project. And so, again, a lot of similarities with the midterm project, but, just take note of kind of the extra kind of requirements that are there. And if you do plan on doing your own geometry, make sure you run it by me before you actually start running the simulations. Okay. Okay. Any questions? Any just overall questions on the final project?
I have one.
Sure.
Will we be meeting on finals week during finals week?
No. So there's no class sessions during finals week, but I will have office hours by appointment during finals week.
Sounds good.
All right, any other questions on the final project here? Okay, all right, so let's talk about optimization. Okay. And so the activity or the theme of the activity this week is optimization. And so I guess it's a little bit misleading to call this an ANSYS activity. We are using the optimization feature within ANSYS, but optimization is actually not a finite element thing. So it's actually not a finite element feature. We just kind of are using optimization together with FEA. Okay. And the reason I'm doing this as an activity is that it's optimization is good to know in general. And the way that ANSYS kind of sets it up is actually pretty nice. And so it's a good feature to know. But I want you to know that optimization kind of extends far beyond FEA. And it has a lot of other applications, but FEA is just a very good application of optimization. Okay, let's go ahead and get started today. So the theme for today is optimization. And design with FEA. Okay. All right, so let me start by saying this. And so, one of the really powerful things about FEA and the reason why it's used in a lot of industry is that it enables what's called iterative design. And so what I mean by iterative design is that it allows you to make kind of incremental or small changes to the design and kind of immediately see kind of what the effect of that design change is. Okay. And so because, FEA is a purely digital platform, you can do things where, let's say that you have a part and say like, let me change the diameter of this part by 3%. Okay. And so you can make a small change like that, and then you can use FEA to see, does that improve your stress distribution, or does that save you on materials? Okay. So it wasn't always like this. And so, if you were a design engineer, working, in the age before FEA, you had to be a lot more deliberate. You had to be a lot more thoughtful about when you made design changes, because it was a lot more expensive to view the changes. Okay? And the reason for that is because if you didn't have a computer, or if you didn't have FEA to test your results, in order to see whether your part was going to succeed or fail, you'd have to build a physical prototype. You either had to build a physical prototype, or you had to do very lengthy and very complicated hand calculations. Okay? And so the difficulties with physical prototypes or hand calculation kind of extended, beyond the fact that it was just difficult to test, right? It was almost impossible back then to know, whether your design was optimal, right? So maybe you create a design, and say that, you make a design for a bridge, let's say, okay? So you design a bridge and you make a scaled down prototype, and you find that it works, okay? And so what that means is that, you apply all the typical loads, you apply all the constraints, you test it under extreme circumstances, and you'll find out that your bridge doesn't break and it's going to last for a long time. Okay. That's great. But, there was no way, or no practical way, to really know if there was any way to make it even better. Right. And so maybe you found a design that works, but maybe if you redesigned a part of it, or maybe if you changed, a certain aspect, you can make it last 40 years instead of, 30 years or something like that. Okay. And so that's the idea behind optimization, is that it's a mathematical framework to basically help you find optimal designs, not just designs that are going to work, but what is the best design? So what's the design that's going to give you the best kind of results in terms of stress and longevity, for the least amount of cost. So that's usually what engineering is it kind of boils down to. So, how can you make parts that how can you make systems that are going to satisfy all the design requirements for the least amount of cost? Okay. So I'm gonna draw a spreadsheet, and so, or not a spreadsheet, I'm gonna draw a kind of a flow chart to kind of show you a typical design process with FEA. Okay. Okay, so usually, usually you got to start somewhere. And so let's say that you start with some kind of initial design. Right, so maybe this is kind of the first concept, kind of the first idea that you have for this design. Okay. And then once you have that initial design, you can go ahead and test it. And so let's say that you conduct a test. Sake of, because this is FEA, of course, you're going to conduct that test digitally using ANSYS or whatever FEA saw. Okay. Right. So once you conduct that test, you're going to evaluate its performance. And so this is the part where you're going to look at the simulation results. You're going to check to see if it satisfies all your design requirements. And so it doesn't break, under a load, all your factors of safety are satisfied, and so on and so forth. Okay. From here, you ask the question. Yes, I'm going to do a diamond here. You're going to ask yourself whether you're satisfied with the current design. Okay. And so after you evaluate your performance, you're going to ask yourself, is this going to work? Is this what you want? Okay. So maybe it does satisfy all your design requirements, but you ask, can we make this better? Can we save some material on this? Can we save some cost? Okay. And so if the answer to this question is no, what you're going to do is you're going to loop around. Okay. And so you're going to conduct another test, but before you conduct another test, what you're going to do is you're going to improve the design. Maybe you change the geometry. Maybe you simply just change the dimensions. You make the pillars, or you make the rods a little bit smaller, a little bit bigger. Okay. And then after you improve the design, then you just conduct a test. Okay. And so you have this kind of loop that's going on. Okay. Eventually, you're going to leave the loop. You're going to reach a point where you're satisfied with the design. And then from there, you are done. So I'm going to box this middle part because this is kind of the main part, or where you're going to spend most of the time in the design process, is iterating, conducting tests, improving the design, and kind of repeating this over and over and over again. Okay. Okay. And so you can do this process manually. And so we did a little bit of this in activity 3. And so you could sit at your computer, you can literally sit at your computer all day and do something like this, where, you make kind of incremental design changes. So, you improve the design, you run the simulation, you see if that improved it or not, and then you make another improvement based on that. And you kind of keep doing this. Okay. And for a lot of kind of, I would say, simpler kind of optimization problems or simple design problems, doing this manually is perfectly fine, because you're able to kind of, do it, fairly quickly. Okay. But, if you have a situation that's a bit more complicated, maybe you have multiple design variables that you're optimizing over, this part here can get extremely tedious and extremely time consuming, right? Even with the computer. And in fact, I would I would make the argument that, for optimization problems that are sufficiently complex, and so maybe you have, 7 or 8 different design variables, I would argue that it's actually impossible to do manually because it's impossible to really explore, all those different design variables. Okay. And so you're going to need a computer to kind of help you out with this. Okay. All right. So this is where optimization comes in. And so the whole idea with optimization is to take kind of this framework, okay, where you're making kind of different kind of small changes to your design and kind of evaluating its performance. An optimization framework will kind of automate this for you. Okay. And so that's basically the motivation behind optimization in ANSYS. And so, in ANSYS, the company that makes ANSYS knows that, a lot of people use it to solve design problems or to test different designs. And so what they've done is they've implemented a lot of optimization algorithms kind of automate this process for you. Okay. And what we're going to learn on Wednesday is we're going to learn the process of, how do you set up an optimization problem? How do you run an optimization in ANSYS? What you can expect from the results, and you'll also get the appreciation of how long it actually takes to run something like this. Okay. Okay. Any questions on this so far? Okay. All right. So from here, I'm going to talk about kind of just the basics of what optimization is, and so that's kind of how it's used for. And so I wanted to start with the application. But it's important to kind of understand a little bit of what's going on underneath the hood, so that you can kind of know kind of what ANSYS is doing, and kind of why it's taking so long. So we're going to talk a little bit about optimization basics, and then we'll talk, and then at the end of today, we'll talk more about kind of how this is actually applied in ANSYS. Okay. So optimization, just like I mentioned before, is not an FEA thing. It's not even an engineering thing. It's actually a math thing. Okay. And so the idea behind optimization, or kind of where it started, it started as a framework to find maximum or minima of mathematical functions. Okay. So as an example, let's say we have a very simple, just 1D function. Okay. So let's say we have a function f of x. On the horizontal axis, we have x. Okay. And let's say our f of x looks something like this. So what an optimization algorithm will do at its core is that it'll look at the function and tell you where the maximum is and what the maximum is. Okay? And so let's say the value of this peak right here is, we call it f opt, okay? And it occurs location x opt. Okay? Okay. And so, of course, for a 1D case, it's extremely simple. And so you can look at this and you can say, I didn't need a fancy algorithm. I could tell you exactly where the optimal is. Okay? And so for 1D, of course, it's not, optimization is not as helpful because you can kind of visually see it, very easily. You can even take derivatives of the function. Okay. Where optimization really comes into play is for multi-dimensional functions. As you can imagine, once you get into 2D or 3D or even 4D, right? There's the whole meme about 4D chess, right? But then you could have functions of 4 variables. And so how do you find the maxima of a 4D function, right? And so you can't really plot a 4D function, at least not with my, human brain, okay? And so optimization helps with that. And it also helps for functions where you can't take the derivative of as well. And there's lots of reasons why a function you may not be able to take the derivative of it. So maybe there's a discontinuity in the function, which makes it impossible to take the derivative in that neighborhood. Or maybe your function isn't a mathematical function at all. Maybe it's just like experimental data. Okay. And so optimization has its place. And so for these kind of weirder functions and these kind of more complex functions, it's a way to find the maximum minima of those cases. Okay. All right, so let's define some terminology in terms of, how to define optimization. Okay. All right, so first let's define input. Another name for an optimization input is a design variable. So that's typically the name that you'll hear me use. And so a design variable or an input of an optimization is basically the independent variables. Okay. And so the exact definition of these are the parameters of the problem that you can directly modify or directly set to influence the output of the design. And so these are going to be the focus of our optimization. And so some examples. So some common examples that you'll see in FEA are things like the dimensions of your geometry, right? So, how big or how small certain parts are, the length of the certain parts. Okay. Because the dimensions of your geometry or the dimensions of your CAD model, that's going to have a direct influence on your results. Okay. Some other things that could be design variables could be like the material. Set up an optimization on the material. And even in some cases, you can have something like the connection between parts, be a design variable as well. Okay. Basically, anything that you have control over that you can actually change in the design that's going to influence the results, that can be an input of a design variable, etc. Okay. And so connecting this idea of the design variable to our mathematical understanding of optimization, okay, The inputs are your independent variables. And so this would be like the same thing as X in the example above. Okay, so let's do a more visual example of an input. Okay. So let's say that we're working on design of a curved pipe. And so our curved pipe looks something like this. And one of the design variables, or one thing that we have control over in the design, is the radius of curvature for this pipe. Okay. So let's say that we have control over R. Right. Another design variable that we may have control over is the diameter. Okay. So let's say that we want to design this pipe, to minimize the amount of material that we use, but to maximize its stability. Okay. And so in this particular case, we have two design variables. One is the radius of curvature R, and 2 is the diameter of the pipe. Okay. So this could be an example of fairly simple optimization with two inputs and two variables. Okay. All right, any questions on this so far? Okay. All right. And so before we move on, kind of I think, the thing that everyone does when you first start doing optimization, it doesn't matter if someone warned you or not. So this is a warning, okay? And so someone warned me too. Someone warned me 3 or 4 different times, but you still do it because you're curious. You have to be careful about the number of design variables that you choose for your optimization. Okay. The reason I say be careful is that the cost of the simulation is going to explode exponentially as you add more and more design variables. It doesn't just grow exponentially, it grows ultra exponentially. So it's hard to kind of overemphasize how much the cost of an optimization grows as you add more and more design variables. Okay, so you have to be really kind of thoughtful about what your design variables are. And a lot of times you have to try to kind of limit it to a certain number so the cost doesn't get out of control. And so if you're usually in the ballpark of like 2 to 6 design variables, it kind of depends on the situation too, but 2 to 6 is usually okay. That's usually something that's reasonable. Seven plus starts to get unreasonable. So that's when things start to get a little bit crazy. So once you start getting into those design problems or optimization problems with 8, 9, 10, 25 design variables, that's when you start to need to use like a supercomputing cluster to kind of help you with the cost. Okay, but for a normal kind of desktop application that you're running here, if you're staying in the ballpark of 2 to 6, you're usually going to be okay. Unless it's crazier than that. Okay. So those are the design variables. Let's talk about outputs. Okay. An output of an optimization procedure is a computed quantity for the system whose values are influenced by the inputs. Okay. And so depending on the values of your inputs, that's going to influence your outputs. Okay. And so, for example, some of the more common outputs from FEA optimization could be things like the total deformation. Maybe you're either looking at the maximum value of the total deformation, so the max deformation in the entire structure, or maybe you're looking at the deformation in a particular part. Okay. Another example is an equivalent stress. Okay, so this is a very popular one. Because a lot of times when you're running FEA, you're interested in stress analysis. You're interested in learning whether your part is going to break or not. Okay, and so equivalent stress is usually something you want to optimize over. Okay, and another common output that we haven't really worked with at all is cost. And so I'm not talking about computational cost in this case, but actual financial money cost that it takes to create the part. Okay. And so, of course, if you design a part with using more material, that's going to cost more money to fabricate. Okay. Whereas if you create a part with less material, that's going to be typically cheaper. But then there's also considerations for the cost of the manufacturing process, the cost of the staff that are involved to make it. So that's kind of another consideration. Okay. And a lot of times this is kind of why you run optimization, because you want to get the design that uses the least amount of material, but still doesn't break under its typical conditions. Okay. Okay. And so just like the inputs, you could have multiple outputs. And so you can test for basically multiple things. But unlike the inputs, you can have kind of more outputs, and it usually doesn't directly, negatively impact your costs. Okay? There are some situations where it does, but and so those might be cases where you have outputs that directly clash with each other. But for the most part, you can add more outputs, and it's not going to have a big impact on your results or on your cost, I should say. Okay. Any questions on this? Okay. So now that we understand what inputs are, we understand what outputs. Let's write a definition for what optimization seeks to do. Okay. And so we talk about what optimization does in kind of a simple mathematical case, but let's talk about what we're aiming to do from a finite element point of view. Okay. And so in a nutshell, what optimization, looking to do is that it seeks to find the values of the input parameters that maximize or minimize an output function. And so next, I'll kind of explain what an output function is, but I wanted to write this definition before we jump into kind of a theoretical example. Okay, any questions on this so far? We jump into an example. Okay, all right, so let's look at a typical kind of case that you would want to do in kind of ANSYS optimization. Okay, so let's look at the optimization of a beam design. Okay. And so let's consider the following beam, which has a load at the end. Okay. It's a cantilever beam. Here's our beams because they're easy to draw. And let's say that it's supporting some kind of load at the end. So we have kind of a load that's being applied P. Okay. And let's write out our design variables. And so, one thing that we can optimize over is the total length of the beam. Okay. And let's say that we also are optimizing over the cross section. So let's say we have a rectangular cross section for the beam, okay, where the height of the cross section is given by H and the width of the cross section is given by W. Okay. And so our optimization problem is posed like the following. And so let's choose or compute the optimal values of L, H, and W. Okay. So those are our three inputs. Those are our three design variables. Okay. L, H, and W. Okay. We want to compute the optimal values for these parameters such that the equivalent stress in the beam is minimized. And the cost of production is minimized as well. So that's our goal. And so we're basically going to be tinkering with these three parameters. And so we're going to be tinkering with L, H, and W, such that the equivalent stress is minimized and the cost of production is minimized as well. Okay. Okay. All right. Any questions on just the setup for the problem here? Okay. Okay. So let's go ahead and set this up. And so we've already established that we have three design variables. Okay. So these three right here are our design variables. Okay. And we have two outputs here. So we have the equivalent stress and the cost of production. Okay. Right. Let me expand on cost of production a little bit because equivalent stress is a little bit easy to kind of visualize. But when I say cost of production, the way that we're going to do this or the way that we're going to compute it is based on the total volume of the beam. And kind of the thought process here is that, you know, if you have a smaller total volume, if you minimize the total volume, that's going to take less material to build, right? It's going to take less steel or less aluminum or whatever, you know, material you're using for the beam. Okay. And so if you can save on material, that's going to save on cost. Okay. Okay. And so since in this case we have multiple outputs, we need to kind of combine those two outputs together into a single kind of score. Okay. Ultimately, you know, the idea with the outputs is that when we compute them, we want to use them to compute a score for our design, right? And so if we make a design change, and so let's say we change the value of L, you know, we want to compare. And so we want kind of a systematic and consistent way to compare whether, you know, our new design is better than the old one. Okay? So think of it like Yelp, right? So if you're deciding where to eat, you know, first thing you always look at now is Yelp to see if it's a good rating or bad rating. Okay? So whether you go to like Taco Bell or whether you go to, you know, real Mexican restaurant. Okay. Okay. So how do we do this? And so the way that we do this is that we form something called an objective function, or sometimes it's called a penalty function. Okay. Oops. Okay. Right, and so there's lots of different objective functions that are out there. We obviously don't have time to go over all the different ones, but let me give you kind of a very popular example, one that kind of ensures that you get a positive result, and one that has some flexibility in it as well. Okay, so for a two output system like this, you know, you may get an output function that looks like this. All right, so this is just one example. So this is what's called a kind of a square or a magnitude version of the output function. Okay. So you can see it kind of closely resembles like a distance function. And so we have a square root. We have you know, our first term there, which is the equivalent stress. We divide that by some kind of normalized stress just to kind of, you know, non-dimensionalize it. We square it, and then we add that to the cost divided by a reference cost squared. Okay. Right. And so depending on the results of the simulation, so depending on the stress that we get and the cost that we get, we can plug them into this function in order to get a score for our result. Okay. Okay. And so you can see here that, one of the things you'll notice that each of the outputs is scaled by a reference value. This is just to kind of make sure that our units are consistent. Okay. Because when you're comparing things like stress and cost, those obviously have different units. And so you can't really kind of either add them or subtract them, just because their units are mismatched. But if you divide them by a reference value, then you basically non-dimensionalize it, and you make it so that you can kind of combine them together. Okay, so you'll see this a lot in a lot of objective functions, just because usually you're working with outputs that have different units, and so typically you non-dimensionalize it just so that you're working with a consistent amount. Okay, and this kind of gives you the opportunity to kind of scale them differently as well. So maybe more so than the equivalent stress, maybe you're more concerned with the cost, and so you can change the value of the reference number. To make it so that cost is more important for your optimization than the equivalent stress. Okay. Any questions on this? Okay. All right, so that's an important concept. And so if this is not something that you set manually within ANSYS, but just know that ANSYS kind of does this for you. And so, you can have outputs that have, very different units. And ANSYS will combine it into a single objective function in this way. Okay, next let's talk about constraints. Okay. Because what ANSYS is going to do, after you've told them, after you told ANSYS, what the design variables are and what you're looking to optimize over, what ANSYS is going to do is it's going to start to run a ton of simulations. So it's going to run a simulation, it's going to change the inputs, it's going to run another simulation, it's going to change the inputs, and so on and so forth. Okay. A lot of times, you want to constrain your inputs so that ANSYS doesn't pick anything that's nonsensical for their values. Okay. Okay. Right, so some examples, it's just even very simply, right? So, when you have costs, and this is always a concern. So whenever you have cost as one of your optimization outputs, ANSYS can be really cheeky and say that, we can minimize the cost. We can have zero cost if you have no beam at all, right? And so if it says that, L is 0 or H is 0 or W is 0, that obviously is going to lead to zero cost because that's zero volume. But obviously that's not a result that you want to see, right? Because you have to have a beam, and so you're designing a beam, you're not designing thin air, right? And so you don't want ANSYS to give you a result like this, right? So you don't want it to give you like a 0 or a nonsensical result, okay? And so to fix this, what you would do is you would put bounds. Often you would put bounds, or you put either an upper bound and a lower bound, or maybe just a lower bound on what you want the values of the inputs to be. And so, for example, let's say the length of the beam let's say that it has to be between 0.8 meters and 1.2 meters. Okay. Right, and so ANSYS is not going to be able to stray from this. And so, when it's choosing its value for L, it has to stay within this range of 0.8 to 1.2 meters. Okay. All right, and then you could place similar constraints on the other variables as well. So, let's say that your height or your width of your cross section, is bound by a certain amount. Okay. And this is useful too, because sometimes, you have other design constraints in terms of how big your part can be. And so sometimes you want to put upper limits to kind of prevent that. Okay. Okay. Sorry, just checking one more thing. Okay. And I mentioned that you can also put constraints on the outputs as well. And so what the constraints on the outputs will do is that it'll basically tell you, it'll basically let you tell ANSYS what are some results that are just, simply just unacceptable. Okay. And so a good example of this is, maybe you have a certain budget for your beam, right? And so you can't exceed a certain budget. Okay. And so if ANSYS comes up with a scenario or comes up with a parameter set where the volume or the cost of your beam exceeds a certain value, you can just say, don't even bother ANSYS. This is not acceptable. We're not even consider this. Okay. Okay. So the constraints are really important, and almost always, whenever you run an optimization in ANSYS, you're going to be placing some constraint. At the very least, you're going to be putting constraints on the inputs, and then possibly some of the results or some of the outputs as well. Okay. All right. Any questions on this? Okay. All right, and so, now that we've kind of reached this point, we've defined all the input parameters, we told ANSYS what our input parameters are. We defined their outputs, we defined their objective function, and we defined their constraints, okay? We're now ready to start the optimization. And so at this point, your work is done. And so, your work as an engineer is done at this point. Now it's just up to the computer to kind of do this for you. Okay. All right. And so now what's going to happen? So now that you kind of defined what we've basically done is we've defined the optimization problem for the computer. Now the computer is going to execute it. And the way it's going to execute it is that it's going to, kind of semi-randomly change the input parameters and run simulations to see, how the outputs change. Okay. Right, and so it's going to run many simulations at this point. So I underline many because the amount of simulations that it runs depends on, depends on the case, right? But a lot of times it's going to be somewhere in the at least hundreds. So it's going to run over 100 simulations in this case. Okay. And the way that and the way that you'll see the results, ANSYS will give you a table that looks like this. And so I'm gonna continue on with this example for the beam, but of course this is going to look different for our activity on Wednesday. All right, so first thing that you'll see is each row. Okay, so we're gonna have 1, 2, 3, 4, 5, okay, and so on and so forth. Okay. So each row of this table is going to represent a different simulation that ANSYS is running or a different iteration of the optimization. Okay. And so let's say that, we're looking at row 1. So that's going to be the first trial. And so let's say that our length here is maybe 1 meter. Our width here is 0.5 meter. Height here is 0.5 meter. Okay. From there, it's also going to show you the values of the outputs. And so it's going to tell you the value of the stress. So that's going to be something. It's going to compute the cost of the simulation for you. Okay. And it's also going to compute the objective value as well. Okay. Okay. So that would be your first simulation. So you would run the simulation with a length of 1, the width of 0.5, the height of 0.5, and then you get all the following results. Okay. And then from there, it would move on to another simulation. So let's say it modified the length. And so it's going to use a length of 0.9, maybe a width of 0.6, and a height of 0.4 meters. Okay. Goes from that. It's going to show you how the results change. So hopefully the results got better. So maybe the stress got better, maybe the cost got better. Okay, the overall objective function got better as well. Okay. But it's going to keep doing this. And so it's going to keep doing this, dozens, hundreds, even sometimes thousands of times. And so, this could take a long time. And so, especially if you have a very high dimensional input space. So let's say you have, 7 or 8 different input variables. This can take a very, very long time. So, but the good thing is that, you don't have to be here during this time. And so you can go to sleep, you can have a snack, you can go watch, you can watch a TV show, you cook yourself dinner. Okay. So all this is going to be running in the background. And so all you have to do is just set up the optimization problem, and then ANSYS will kind of handle the rest for you. And so it'll choose what parameters to run, it'll track all the results. And at the very end of the optimization, you will have, a certain row of this table that gives you the optimal result. Okay. And so let's say at the very end, let's say we have, this row here was our optimal result. Okay. Okay. And so what the optimal result will tell you is that, that's what you should design your part after. Okay. So those are the best dimensions. So that's going to save you the most cost, and it's going to, have the least amount of stress as well. Okay. All right. Any questions on this? Okay, all right, so I'll leave one quick note before we go, just because we have a couple minutes. And so you may be wondering, all this sounds good. But how does, you may be wondering, how does ANSYS choose the parameters, right? And so the way I've kind of described it here is that, it kind of seems like ANSYS is just kind of changing the values of these parameters at random. And it may kind of seem like that when you're first watching this, the optimization unfold. But there is a method to the madness. There is a way to, for ANSYS to select these parameters in a way that gets you, closer to the result. Okay. But the theory behind that is kind of way beyond the scope of this class. And in fact, a lot of times you have to take kind of a dedicated optimization class for that. Okay. But in case you're curious, and in case you wanted to kind of read up on it on your own, the whole idea or the whole theory behind, choosing the parameter values is called the optimization algorithm. Okay. And so there's lots of different algorithms out there. In fact, there are probably thousands of different optimization algorithms out there. Everyone, for some reason, it became very trendy for a while to try to make your name as a researcher by developing your own optimization algorithm. And so there's a lot. There's some that are more general purpose, that are some that are more niche in certain situations. But you can kind of look those up on your own. Okay? And so sometimes, if you have kind of a weird or complex optimization problem and you're not really getting good results, you can try changing the optimization method and see if that kind of improves your results. But for most general purpose, I would say you're not going to see that much of a difference between the different methods. It has to be a pretty niche situation in order to see the difference. But there is a method, there is kind of an algorithm that ANSYS follows to choose the parameters. It's just that, we just don't have time to go over it. It's super interesting, but it's kind of beyond the scope of this class. Okay, all right, so that's all the time that we have for today. And so next time I see you guys will be on Wednesday for ANSYS Activity 6. Okay. And so thank you guys for coming today. I hope you guys enjoy the rest of your evening. And I will see you on Wednesday.
Thank you, Dr. Chan.
Oh, yeah, sorry. I was going to Zoom.
What value assumes you get.
What do you mean?
So Linus taking almost 20 minutes to solve one.
It is like that sometimes. As long as you're consistent. So as long as you pick kind of the same one. Usually, traditionally, people will like the max, the absolute max. But I think as long as you're consistent with it.
So like, because what happened now is, I realize that changing the application is slow. This is the value when I actually did not solve the given value, right? So
Yes.
What I've got.
Yeah.
But when I play, I get a different value. I don't know both values are.
Okay, no, as long as you're using the same one for each one. And I think whatever it shows you by default is gonna be the same. As long as you're using that one consistently for each of your questions, then that's fine.
But I don't know, it's
That's typically that's gonna be the case, especially because remember we're using we need to catch a keeper as well. So it's gonna be difficult. I'm not looking to see if your result actually converts. That would actually be very difficult, especially for this is a very difficult piece. You can hear elements. And it's very, very passive. And so I don't expect, unless you're doing a very, very small, I don't expect it to convert. So if you show me this plot right here, that's perfect. I'll give you that. Yeah, you don't have to reach this. And that goes for the final project as well. We are so limited in terms of the density. And just for a lot of problems, it's just not going to be possible. The conversion point is really going to be way up there, and we can't do this. I do want you guys to go through the exercise again. Yeah, no, that's really good. That's equivalent stress. Oh, yeah, no, that's exactly what I would do. Yeah, but that doesn't always happen.
Because I tried doing all these codes,
Yeah.
all these for computers, every computer got different values.
Yeah,
So.
there's a little bit of randomness in it too. It's usually not high amount of randomness, but it's. Yeah, but it looks good, both of these. Look. Yeah, cool. Yeah. Oh,
Oh,
oh, thanks. Yeah, have a good night.